Okay, so graphs gone wild. That's chapter 2 is all about graphs. And there are two kinds of data. This is the review part. Quantitative data, which we already know about, and qualitative data, which we also know about. Quantitative data is numbers. And we're going to start out with quantitative data and using a small data set, which means the data set doesn't have a lot of values or really large, complicated numbers. We're going to learn how to make something called a dot plot. The dot plot is one of the methods in statistics referred to as the quick and dirty methods. You don't necessarily need a computer or anything else to be able to do these two methods that I'm going to show you today. And this actually is the last thing I think we need to learn in chapter 2. The dot plot actually keeps your data values retrievable. If you make a frequency distribution and you label it with the midpoints, your data are no longer retrievable from that frequency distribution. Or if you even use the class limits, the data are no longer retrievable. You can't look at that frequency distribution and say, oh, I know what those numbers were, because all it says is you had 5 numbers between 0 and 9. You don't know what those 5 numbers were. But in the dot plot, we can actually get the data back. Now, if the data set were to be large, or you have the range is particularly large, very large, or there's too many data values, then you don't want to use this method, because it's only good for small data sets that have a small range. You don't want numbers that range from 1 to 100 and have 1 1 and 1 that's 95 and then everything else is between 30 and 40. This method doesn't work well for that. So here's what we're going to work with. And this is the 2-page that I gave you to take notes on. Tuition costs in thousands of dollars for 25 liberal arts colleges, what we have here. Okay? So what we're going to do is we're going to make a dot plot, and it doesn't take too much trouble to look and see that the smallest data value is 15. And as you skim through these, you'll notice that the largest one appears to be 30. So what you want to do is you want to draw a number line that goes from 15 through 30 and list every number in between. Now you don't necessarily have to mark every single tick mark. Notice here that I started with 15. This is 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Okay, so it's just like you were going to draw a graph, like a two-dimensional graph in algebra and plot points, except it isn't going to be plotting points by having the second coordinate. There's only going to be one coordinate here for all of these. Okay? Now, if you look, the very first number there is a 23. So notice that that puts a dot over where the value 23 is, just one dot. The next number is 25. Okay, there's another 23. Logically, that should have been 25. And then there's a 30. I'm sorry, 23. Yes, hang on a second. I got to fix that. That's going to drive me nuts. They're out of order is what the problem is. Maybe that'll do it. Okay, so we start out, we've got 23. Yeah, there's another 23. That one just popped up too soon. The next one actually is 25 and then 30. So that's the first 4 values. Now what you do is you just keep putting them on And notice that every time a dot pops up, it corresponds to one of the numbers that's up there. So this is the first 30, and then this is the second 30, so we put it up a little higher than the first one. And then there's 1, 2, 3 25s, one for that one for that one, and then one for this one. And then there is a 15, because we haven't come to the other one yet. And then there is 120, and there's a 22, and a 21 for these two. And then there's a 24 for this one. So you just keep adding the dots as you go through your data. One dot for each value. Oops. Now, notice here that this has the same kind of characteristics as what you would see if you had a histogram, right? We learned how to make a histogram already. The good thing about it was we didn't find any class limits. Didn't need to. We didn't have to calculate a class width. We didn't need to. We got the same kind of information we would have gotten from the histogram, which basically is that there's only one 15, while there's 3 30s. Those are your two extremes. But you notice that most of your data is around in this area right here, which tells me that probably the mean is somewhere along in here. Now, if we actually calculate up all those numbers, we would know exactly where the mean is. And I want you to always be thinking about that. So just, even though it's not really part of what we need to do right now, I'm trying to blend in chapter 3 as we go along rather than leaving it all out there by itself. So let's see. Go to this. I'm going to go to my calculator now, and I'm going to put in some data. And since I know I have more than just the 5 numbers I see in my list 1, I'm just going to type over the top of them. 23, 25, 30, 23, 20, 22, 21, 15, 25, 24, 30, 25, 30, 20, 23, 29, 20, 19, 22, 23, 29, 23, 28, 22, 28. So there's my 25 numbers. And if I want to calculate numerical statistics, and if you haven't come to this part in 0530 yet, you will, so I'm trying to give you a little heads up here to keep us kind of on an even keel. We can calculate the numerical statistics. We've done this before too, but we only looked at the median and the mean, and then we tried to figure out what the mode was. So here, if we calculate one variable statistics on those numbers I just put in list 1, it says the mean is 23.96. And the reason the mean is 23.96 is because if you add up all 25 of those numbers and then divide the sum by 25, they add up to 599. And 599 divided by 25 is 23.96. Now, when you report that mean, this is a sample of liberal arts colleges. This is not a population. So the correct symbol you're going to use is going to be called X bar equals 23.96. You're not going to round that off to 24. You keep it at 23.96. And then some other measures of variability we'll look at are going to be the standard deviation, either the sample, which this is, or a population. And the median data value is 23. Okay? So the median and the mode, notice here, is also 23 because there's more dots over 23 than anything else. So right about here is where the mean is. There's the median and the mode. Now we're going to look at the other one. Another quick and dirty view of the shape of the distribution is called a stem and leaf plot. On this little vine here, you've got a stem and you've got leaves coming off of each stem. Again, this one keeps the actual data values retrievable. You'll be able to actually pull the data back out of the graph. But you have to include a key with that graph that explains what each value is. And I'll show you how to do that. And these are things that you would make by hand. You wouldn't necessarily want to make them on a computer because it's a small data set. So you don't want to have to haul out a piece of equipment to be able to do something when you only got about 20 or 25 numbers. So here we've got test scores for 15 employees enrolled in the CPR training course. It's 13, 9, 18, 15, 14, 21. You can glance through there relatively quickly and see that the lowest score was a 5. I don't want that person working on me. Probably you don't either. And the highest score appears to be 37. So that person did an outstanding job on the test. And then the other values range somewhere in between. So in order to make what's called a stem and leaf plot, we have a stem and leaves. The stem and the leaves correspond to digits in the number. Each one of these numbers is either a 1 or 2 digit number. So we're going to take the stem to be the number that is in the tens place. So the stems are going to be 0, 1, 2, 3 because numbers like 9 and 7 and 5 actually have a 0 in their tens place. 0, 5 is the same as just 5. 0, 9 is the same as just 9. So the 0 is a placeholder. But then some of the data have 1 as their tens digit, like 13, 18, 14, 15, so forth. Then we have some numbers that are in the 20s. They have a 2 for their tens digit. And then we have some numbers, actually only one, that has a 3. Okay? So what we do then is the leaves are the numbers in the ones place. So for example, 13 is listed as 1, 3. It goes on the stem for 1, and then you put 3 in the table after it. So then there's 9, 0, 9. Then 1, 8, then 7, and then 5. And there's the whole thing completely filled in with all the digits. And what I want you to notice here is that 3, 7 represents 37. And 1, 7 represents 17. That means we have a 21 and a 20. Okay? So we could recover those numbers from the graph itself. And notice here too, what would happen if I were able to just peel that off of there and turn it, instead of going out across the page, what if I turned it up? It's a bar graph. It's a nice little bar graph. Or histogram, seeing as how it's numerical data. Okay? Remember, the difference in a bar graph and a histogram is the bars on the histogram touch, the bars on a bar graph have a little gap in them. Okay? But we can get the data back off of that graph. So I don't even have to look up here to enter in the numbers. I can go for the graph and enter on the 0, that's 9, 7, 5. And then on the 1s, I've got 13, 18, 15, 14, 10, 11, 18, 16, 17, 21, 20, 37, and then I'll just delete the rest of the numbers that were there, because that goes with the other data set. And again, if I calculate, I see that the mean is 15.4. Well, it makes sense that it would be, because this is the tallest bar, so I would expect to see the mean where the most of the data is, and it would be within those numbers right there. And if I rank order them and put them in the middle, I would see that 15 is also the median. Now for the mode, the stem and leaf plot works. It actually works pretty well, because you can look across just that one group and say, okay, here's an 18 and here's an 18, so there's two 18s in the data set. Nothing else is showing up twice. So the mode is 18, not 15. Okay? Now, the only difference in this graph and the one that you saw just a minute ago is this is called an ordered stem and leaf plot. Basically, rather than leaving them all jumbled up, we just put all the numbers in order. So this is 5, 7, 9, 10, 11, 13, 14, 15, 16, 17, 18, 18, 20, 21, 37. Now, hopefully that'll be the easiest thing you've done in statistics class so far. So that's the last two of the charts that we look at in Chapter 2. Now I'm going to quickly look over quantitative data. Let's see, we already did that one, so I need to close that one. And we're going to look at quantitative data. Well, I've got that one misnamed. We've already done large sets, though. Okay. So this is minutes spent on the phone, and this is just review. I'm sorry, to 3, not 13. My goodness. So here, we're not talking about large data sets anymore. We're talking small data sets anymore. We're talking about a bigger data set. Things that have more than 25 pieces of information in it. And when you start looking at bigger data sets, when you're trying to figure out anything about them, you know, like what the mean is, what the median is, or, you know, kind of like what the typical piece of data looks like, it's like looking for a needle in a haystack. You know, you're going to find it, but you're going to work on an awful lot to do it. You're probably going to have to take apart the whole haystack. And this guy says, congratulations, it only took you 65,298 seconds to find the needle in the haystack. Wonder how long that is. So if we want to make a frequency distribution with 5 classes, just a quick review, what do we need to do first?
Class width.
Okay, and how do we get class width?
Maximum plus minimum divided by student.
Maximum minus. You got midpoint. Okay, that's the midpoint. Yeah. That's actually called the mid-range, what you just told me. It actually does have a name. So the maximum minus the minimum and divide by the number of classes. Can anybody fairly quickly pick out the maximum?
125.
Okay, 125. And the minimum?
71, 67.
Yeah, 67. I would say 71, but then you have to keep looking at 67. Okay? So we could load it into the calculator, but we were actually able to find it with a relatively not too large set of data. We can actually find it almost as quickly as typing it in the calculator. So the maximum is 125 and the minimum 67. So the way that we find class width is we take the maximum minus the minimum. That's actually called the range. And the range of the data set is 58. And since we want 5 classes, our class width is 11.6. Now, how many decimal places did the data have? None. So what should we do with 11.6? Round it up to 12, because 12 has no decimal places. Now, if that data had one decimal place, then we need to round up. In this case, it might have been to 11.7 rather than all the way to 12. It just depends on looking at your data. How many decimal places does the data have? That's what you want to set your class width to, is that same number of decimal places. So, you build class limits, beginning with the minimum data value, which was 67, and you add 12, and get 79. And then you add 12 to 79, and you get 91. And then you take 91 and add 12, and you get 103. When you add 12 to 103, you get 115. So I'm going to kind of cut to the chase a little bit, since we've already done this, and this is just review. We're going to get our upper class limits the same way. And then we're going to go through those numbers and count. And eventually we're going to figure out that there were 3 numbers between 67 and 78, and 5 between 79 and 90. And 91 to 102 we had 8, and 103 to 114 we had 9, and then from 115 to 126 we dropped back down to 5 again. So this tells us that most of our data are between 91 and 114. And that tells me that if I were to have calculated the mean for those minutes spent on the phone, that I would have expected that to be probably around maybe 100, 102, 103, because it should be around midway between these two numbers, because that's where the most of the data is. So then we take that frequency distribution and we learned how to do relative frequency and cumulative frequency. We took the frequencies, and to get relative frequency, we had 30 pieces of data, so we divided the 3 by 30 and got 1/10 or 10%. 5 over 30 was 0.167 or 16.7%, and so forth. And when you add up your relative frequencies, they should add up to either 1 or 100%, because that's 100% of your data. Cumulative frequency does what cumulative tells you it's going to do. It accumulates as you go down the chart. So you're going to start out with 3, and then 3 plus 5 is 8, and then 8 plus 8 is 16, and 16 plus 9 is 25. And 25 plus 25 is 30, and that should be 30 because that's the complete sample size. So the sum of your cumulative frequency should equal your sample size. And then we talked about getting class midpoints. A lot of times if we're going to do any calculations with the data from a frequency table, we need to know the midpoints to be able to estimate what those first 5 numbers were, or those first 3 numbers were. And it's the only way you can enter it into a calculator if you don't have the table, if all you've got is the frequency table and you don't have the numbers themselves. So the way you get the midpoints is you add the lower limit plus the upper limit and divide by 2. And then after you've done the first one, since you know the class width, you just continue until you fill them all in by adding 17 each time. I'm sorry, not 17, 12. And then you could make a histogram. And just to review, a bar chart of quantitative data is a histogram. The difference is that the bars touch in a histogram. They don't touch in a bar chart. The things you want to be sure and have when you make a graph for me is you want to either label the midpoints or the class limits underneath the bars. The midpoints are usually just as good as the class limits, because you could figure out what the class limits were if all you have is the midpoint. You want to tell me what that axis represents, and you want to give your graph a title. So there's where the review ends. Now we're ready to move on, and I will show you this. I haven't put it in there yet, I don't think, or if I did, I haven't had you open it. But this is your homework to do. I want you to get plenty of practice making frequency distributions. So this is your homework to do for Chapter 2 for tonight. I've given you some data for wild bears. This is the weight in pounds of wild bears between the ages of 8 months and 177 months. What you want to do is you want to make a frequency distribution of 6 classes. And that's a quick summary right there of what all your other definitions are. And then this data is the same bears, but it's their body length. So you want to create a frequency distribution here of also 5 classes. But not 6 this time, only 5. Okay? And then I want you to look at that frequency distribution and fill in the blanks on the bottom. So that'll be in this same file, same folder on Shobi. Okay. So we're going to start out I'm going to remind you of what the measures of center are. These measures of center in some textbooks are also called measures of central tendency. And then measures of variation are also sometimes called measures of spread. So it's about how the data are spread out. So the mean is what is all this is not what we usually call it, but it's the arithmetical center. Another word that's used for it is sometimes called the geometric center. The median is the physical center, and the key to remember here is that your data must be rank ordered. And then the mode is the one that's the most common, and the other word for that is it has the highest frequency. And we could also say it has the highest count. Since a frequency is actually a count. Now the third one, the first three are all good measures of center. The last one is listed in your book. It is actually the most useless one, but it's really easy to find. The mid-range, if this is your data set, and you've got a min and a max, the mid-range is the number that's right dead center between those two numbers. So it's basically the midpoint of the range. So it's easy to calculate because all you need is the smallest and the largest data value, which you can just look at your data and find, and then add them together and divide by 2. But the problem with it is, for all the work that you did to get it, it's probably the most useless piece of information on the planet because it only takes into account what 2 pieces of your data look like. And if most of your data is pretty far away and more clustered up in the middle of that, then that mid-range might be good. But if you've got data that looks, kind of like this, and then your highest number's way over there, it's going to tell you that your mid-range is probably one of the largest numbers in your data set. And of course, that's not a measure of center at all. So there's your measures of central tendency, or measures of center, which we've already looked at. We know how to get those on the calculator. Now we'll move on in this chapter, although not immediately, to measures of variation. Measures of variation are, first of all, the range. And that's, again, max minus min. And then we have something called the standard deviation. And it's actually the most useful of the numbers, but if you had to calculate it with a formula, the formulas tend to be ugly and they don't necessarily show you a lot about why the number measures what it does. But it measures the dispersion within all of the data values. It compares them all to each other and to the mean. And then the variance is a measure of spread that's related to the standard deviation. It's the square of the standard deviation. It doesn't measure anything that we have any intuitive understanding of. So I'll expect you to understand or remember that the variance is the square of the standard deviation, but that's all. You don't have to calculate it. Now here's our first example. What we have here is the price in dollars for a sample of room air conditioners, 10,000 BTU per hour air conditioners. And we noticed that the prices range from a high of $840 to a low of about $420. And there's only 5 of them, so we don't have too many data values to deal with. The first thing we want to do is we want to find the mean, the median, the mode, and the mid-range. Okay? So if we find the mean, just not necessarily how to compute it, but you need to know the process. So I'm going to remind you of the process. To find the mean, and this is a sample, so its symbol is going to be X bar for the mean, is 500 plus 840 plus 470 plus 480 plus 420 plus 440. So there's the sum of the data values divided by 1, 2, 3, 4, 5, 6, 7. So there's 7 air conditioners. Now, don't calculate that yet, just write down that that's what it is. I'm not expecting you to do the arithmetic. The mode and the median does not have a symbol, although your calculator calls it MED. For the median, we actually have to rank order those air conditioners. So we'll start with the smallest one, 420, and then 440, and there's two 440s. And then 470, and then 480, and then 500.
No, I'm looking at, sorry.
Yeah, there's 140, but there's two 440s. And then there's an 840. So if we're trying to count the middle one, then we go from the ends toward the center, and we find it's 470. Or you count how many data values you have, 1, 2, 3, 4, 5, 6, 7, and know that 7 over 2 is 3.5, which tells me if I go 1, 2, 3, this one actually belongs to the upper half and to the other half. It is the middle. You'd have to round up if you've got an odd number of data values. So it actually would be the fourth data value in a rank ordering scheme. And since we've already rank ordered, now it's easy to find the mode, because it's the one that shows up the most often. So it's 440. Now, using the calculator right quick, because it doesn't take long, and this saves us having to do arithmetic in case we want to do anything again. We're going to go Stat, Edit. This time I'm going to clear them out. In fact, I'm going to clear all of them out. And if y'all try to do what I just did, be very careful, because the word, when you put that cursor on top over L1 or L2, the key you want to tap is clear, not delete. Clear means shake it out, throw it in the trash. Delete means take it away. I don't want to see it anymore, which is what it does with your list. It takes it away and doesn't show it to you. Okay? And when you've deleted all your lists, that's when people usually panic and say, I've broken my calculator. So use the delete button actually down in the list. That's the safest way. So we're going to enter in those data values: 500, 840, 470, 480, 420, 440, 440. And then I'm going to go Stat, right arrow to Calc, choose one variable, Statistics. The only list I'm using is list 1, so I don't have to tell it which list it's going to assume it's list 1. And it says the mean is $512.85. Well, actually 86 cents. We're going to be more accurate because we round properly. It would be 86 cents. Okay? Now let's look at something here. Our smallest data value was 420, right? And our largest data value was 840. So if I go 420, 30, 40, 50, you're going to have to plan carefully if we're going to do this. We need to get 420 in, but we also need to get 840 in. So I'm going to let this be 400, 20, 40, 60, 80, 500, 20, 40, 60, 80, 600, 20, 40, 60, 80, 700. 20, 40, 60, 80, 800. 20, 40, 60. Okay? Now, what I want you to do is I want you on that number line, and you could have scaled it a little differently even from me. You could have gone by 25s if you wanted to. But you clearly can't go by 10s. Okay? Where is 512.86 on that number line? Approximately.
Pretty much right after 500.
Yeah, it's not too far past the 500. Because if this is 500 and this is 520, it's a little bit off center between those two marks. So there's your mean. Agreed? Where's the median? This is 400, this is 500. Where's the median? That's 470. The physical middle is 470.
It's right in the middle between
460 and 480.
Yeah.
And I'm going to put MD for that, for median. Okay? Where's the mode? There's your mode. Okay? Mode, median, X bar. Does that look like the center of the data to you? Nope. Because if I put my min and my max in here, remember my minimum was 420. And my maximum was 840. So there's the box with all of my data in it. But the mode, the median, and the mean are all down on the low end of that. Okay? Notice though that the one that's closest to the center is the mean. And the reason it's closest to the center is what we're going to look at next. So I'm going to go ahead and I'm going to label exactly the same way on the next line. I'm going to start at 400, 420, 440, 460, 480, 500, 420, 440, 460, 480, 600, 20, 40, 60, 80, 700, 20, 40, 60, 80, 800, and I'm going to redo the mean, median, and mode for the data set, but I'm going to do one thing. I'm going to reroute the data set down here so you can see it. So there's the data set. And this is what we're going to do differently. Do you think that if there are air conditioners out there available for $420 through $500 in the majority, how many people are gonna pay $840 for that same air conditioner? No, that's just people that want the Cadillac of all air conditioners, right? So we're gonna omit that highest value and recalculate. Now, we're not throwing it out, we're not saying it doesn't exist. But I want you to see what it does to your measures of center. So if we toss that one out, then here's our new mean, median, and mode. We're going to start with the mode. Did the mode change?
No.
Nope. Usually the mode doesn't change if you take off the extremes. So the mode's still 440. Did the median change?
Yes.
Yes, it does, because now we have 1, 2, 3, 4, 5 numbers. I'm sorry, I left out one. 1, 2, 3, 4, 5, 6 numbers. So that means that my median is halfway between 440 and 470. Right? Well, halfway between 440 and 470, I could get that by doing the midpoint. 440 plus 470 divided by 2 is 910 divided by 2, right? Which would be 455. So my median is 455. Okay, there's 20, 40, 60, 55 is probably right here. Now I need to recalculate the mean. And unfortunately, the calculator makes that easy. I just go back to stat, go back to the data, go find that overpriced air conditioner and delete it. And then go back to stat and over to calc and choose one of our stats and find that the new mean is now $458.33. Let's see, $458.33. If this is 440 and 460, it's right about there. Now what I want you to do is to compare. Did the median change? A little bit. Did the mode change? Nope. Right where it was. Did the mean change?
Yes.
A lot. Because remember, it was up here. Now it's down here. Why did the mean change?
Because you removed the 40.
Because I removed the 840, and the 840 contributed to the sum of all the data values a lot more than any of the other numbers did. So by removing it, it allowed the mean to move closer to where most of the data values were. Okay? By definition, that 840 is what in statistics is called an outlier. It will lie outside the range of most of your data values. Okay? Let's continue working with those ideas. We now want to get into something called standard deviation. Notice we didn't, oh, and I did forget to have you calculate the mid-range. So let me go back and do that. The mid-range of that data set would be 420 plus 840. I'm sorry, not plus 840, it will be minus 420, 840 minus 420. Divided by 2, so that would be 420 divided by 2. Now it doesn't make any sense. I am truly losing it. You add, not subtract. So 8 and 4 is 12, 1260 divided by 2, which would be 630. Do we even have an air conditioner in there that costs $630? No. But it would be right here. There's your mid-range. All your other data is down here, from 500 down. You got one more value up here and there aren't any 630s. But now if I leave out that 840, my mid-range changes. My mid-range becomes 420 plus 500, which is 920 divided by 2, which is 460. So 460 is right there. Now it's right down there in the middle of the other measures of center. Right, it's close to all of them. So why is it that we are so suspicious, especially of the mid-range as a measure of center? Look where it wound up. Because the only things it looked at was the 840 and the 420. It paid no attention to anything else. It only used 2 of your data values. So either one of those 2 data values has a large, like 50% of the influence on it. So you want to be cautious of the mid-range. Now I want to talk to you about standard deviation. And I don't want us to calculate it. What we're going to do is we're going to compare all these sets of data here. And we're going to assume the data sets are all populations. So whatever we have, those 4 values are all there is. And we're going to find the mean and make a dot plot of that data. We're going to put an arrow where the mean would fall on the x-axis. Then we're going to find the range. And then after we've done all of that for all 3 sets, then we're going to find standard deviation. I want you to develop a concept here. So here's my dot plot. I'm going to go 0 through 10 on those lines. And I've got a 5, and a 5, and a 5, and a 5. Okay? What's the mean? So 4 5s is 20. 20 divided by 4 is there's X bar. Okay? What's the range? Zero. 5 minus 5 is 0. Doesn't matter which two 5s you pick, they're all 5s. We're not going to find the standard deviation just yet. 1559. 1 and 5 is 6, 6 and 5 is 11, 11 and 9 is 19, 11 and 9 is 20. Over 4, the mean is still 5, agreed? Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The mean is 5, but here's the numbers. 1, 5, 5, 9. So what you have now should look like that, right? What's the range? But the mean was still 5. Now let's look at the ones on the bottom. 1 plus 1 is 2, 2 plus 9 is 11, 11 plus 9 is 20, divided by 4, which is, again, 5, right? And the range is still 8. But here's what our data set looks like. I've got 2 1s, and then I've got 2 9s. But the mean is still 5. So look at the big picture here. All 3 of those data sets have the same mean. Set 2 and 3 have a larger range. And set 1 has a range of 0 because it's all the same data values. Now we're going to find the standard deviations of all 3. And it's actually not going to be hard to do that. And I'm going to tell you how you actually do it without putting it in the calculator. And the arithmetic is going to be easy enough that we can do it by hand. So what we're going to do is we're going to take all of our x values, which are all 5, and we're going to subtract the mean from every one. And since the mean is 5, that's going to be 5 minus 5. Which means that value on each case is going to be 0. And then what we're going to do is we're going to take that quantity, x minus x bar, and we're going to square it. 0 squared is 0, 0 squared is 0, 0 squared is 0, 0 squared is 0, and then we're going to add it up. That ought to be easy enough. 0 plus 0 plus 0 plus 0 is 0. And now that we have the squared differences, we're going to divide by 4, which is still 0. And then we're going to take the square root of 0, which is 0. That is the standard deviation. The standard deviation for your first data set is 0. Now we're going to do the same thing for the second data set. Second data set, the x's are 1, 5, 5, 9. And I already know how this is going to play out. That's going to be 0 and that's going to be 0. And when I square those two, it's still going to be 0. But what about 1 minus 5? Because remember, I'm subtracting the mean. What's 1 minus 5? Negative 4. And then negative 4 squared is 16. Not negative 16. Negative 4 times negative 4 is positive 16. What's 9 minus 5? And 4 squared is 16. So here's all my differences. And like I did before, I'm going to square all those differences. So these are the squared differences, and then I'm going to add them up. 16 plus 16 is 32, plus 0 is still 32. 32 divided by 4 for 4 differences is 8. And then we take the square root to get s. So it's the square root of 8, and for that I want a calculator. And it's 2.828. Usually Pearson has you round to thousandths, so we'll round that one to thousandths. So it's bigger than 0. Does it make sense it would be bigger than 0 if we're measuring spread? Yeah, because I've got one here and a couple here and then another one way up on the other end. So the spread was quite a bit bigger. Now let's do the last one. So my x numbers are 1, 1, 9, 9. And x minus the mean is 1 minus 5, which is, okay, and this one's also negative 4. This one's 4, and this one's 4, right? And when I square all these numbers, what do I get? Every single time. So when I add those up, $16 plus 16 is 32. That's another 32, so that'll be a total of 64. Then I'm going to take that and I'm going to divide it by the 4. And 64 divided by 4 conveniently is 16, right? And what's the square root of 16? It's 4. This standard deviation is 4. Okay?
What is it supposed to represent? Is it just representing the spread?
It's representing the spread overall of your data set. Okay? In other words, this one was 0, which if you look at it, it kind of makes sense. Because there was 0 spread. All of the numbers were the same. But we got a little bit bigger standard deviation when we took out 2 of the 5s and put in a 9 and a 1 in their place. And then we got a lot bigger spread because now my data is stacked on 2 ends. There is no middle in there, even though the mean is 5. Okay? And the mean, the median, and the median are both 5 actually. In fact, it's both 5 in every single case. Not only is X bar 5, but the median is 5. So it's saying that if your data are very close together, or perhaps not any different from each other at all, then your standard deviation is going to be very small or 0. But if your data values are spread wide apart from each other, then the standard deviation is going to be larger in relation to how far spread apart they are. Now the last thing we're going to do is go back and look at those air conditioners again. And what I'm going to do is I'm going to recalculate but I'm going to put the 840 back in there. And the standard deviation on those air conditioners with the outlier still in it is $146.82. Okay? Does the outlier influence the spread of those data values? Yes, it does. It makes the range a lot bigger. But if I remove the outlier, so I'm going to go back and take it out again and recalculate. What's the standard deviation now? So $29.94. Now look at the difference in the standard deviations. When you include the number that's way far away from the others, the spread is huge. And your standard deviation is $146 and change. But if you don't have that one number, if you take out that one number and look at the rest of the numbers, they only vary from each other by about $30. Not $146 and change. Okay? That's what standard deviation measures. It measures the spread of all the data. But when some of the data values are really large compared to the others, or if they were really small compared to the others, then the standard deviation is going to be a lot bigger with the outlier included. So what we're going to do next time is finish up chapter 3. We're going to talk about something called box plots. Seems like we're going to be going back to chapter 2 again. And in fact, we are. We're going to make a couple more graphs. And we will be done with chapter 3, and I will have a practice test that I'll have ready to post for you. Okay? Anybody has any questions, be sure and watch Shelby because I'm going to post some homework